Welcome to the CSUN video learning module on limiting reactant problems. My name is Simon Garrett. In this video we'll work through some problems that frequently confuse students. These are examples where you're asked to find the amount of a product when one or more of the reactants is in short supply. It limits the maximum amount of product that can be made, so it's called the limiting reactant. It's easy to understand in concept. Suppose we want to make as many fast food meals as we can, each one consisting of a burger, a portion of fries, and a drink. How many can we make? Clearly, we are limited by the portion of fries, and although we have enough burgers and drinks to make more meals, we've run out of the limiting ingredient, the fries, after 2 meals. We can make no more. You've just done a limiting reactant problem, but whereas this one was straightforward, chemical limiting reactant problems usually can't be worked out without some calculations. So you might need a calculator here. You should review your notes and textbook, especially on stoichiometric equations and mole ratios, before starting this video. Here comes your first problem. Question 1. How many molecules of sulfur trioxide can be made from 2 molecules of sulfur dioxide and 3 molecules of diatomic oxygen according to the balanced equation 2SO2 plus O2 making 2SO3? Stop the video here and work out your answer. Before we start, let's analyze the question. What are we asked to find? What information is given? We're asked to find the number of molecules of SO3 and are given the number of molecules of SO2 and O2. I'm going to label them in the question so we can keep track of them. But we might have a more general question. How do I know this is a limiting reactant type of question at all? There's no clue in the question, and without such information, we should assume that all stoichiometry calculations like this could involve a limiting reactant, in which case we need to figure out these type of calculations quite often. Our first step is to write down mole ratios, one for each of the given substances. Each mole ratio will contain one given substance and the unknown. The first one looks like this. SO2 is a substance about which we know amounts, so it's a given, and SO3 is the target of our calculations, the unknown amount. Where do these numbers in the mole ratio come from? They come from the balanced chemical equation. This 2 is the coefficient before the SO2, and this 2 is the coefficient before the SO3. Again, we have 2 givens, so we can construct 2 mole ratios. Here's the second one. It contains a given and an unknown. The 1 comes from the invisible coefficient before the O2, and the 2 from the coefficient in front of the SO3. Remember, we don't yet know whether these are the correct mole ratios. We may end up using their upside down versions. Our next step is to use each of the mole ratios in conjunction with the given information to calculate the amount of product made, assuming the other reactants are plentiful. The chemical term for plentiful is in excess. Here's the first calculation. We have used the given amount of the first reactant, SO2, and multiplied it by a mole ratio that contains SO2 and the unknown. Actually, this is the left-hand mole ratio above, but flipped upside down. Notice how the units cancel? This is really just a unit conversion problem. Working the math gives the answer 2 molecules of SO3 can be made from 2 molecules of SO2. Here's the second calculation. We have used the given amount of the second reactant, O2, and multiplied it by a mole ratio that contains O2 and the unknown. This is the right-hand mole ratio above, but flipped upside down. Again, the units cancel as they should and give us the answer that, if everything else is in excess, we can make 6 molecules of SO3 from 3 molecules of O2. We've finished the calculations. What do these two answers mean? Clearly, from the amounts that we're given in the question, we only have enough SO2 to make 2 molecules of SO3. So it's the limiting reactant. Our final answer is 2 molecules. Confused? Let's try another one. How many molecules of CO2 can be made from 140 molecules of C3H8, propane, and 140 molecules of diatomic oxygen according to the balanced equation C3H8 plus 5O2 making 3 CO2 and 4 H2O? Pause the video here, work on your answer. Let's analyze the question before we start. What are we asked to find? What information is given? We're asked to find the number of CO2 molecules and are given the information regarding the number of molecules of reactants, C3H8 and O2. Again, I'll label them to keep track of them. Our first step is to write down 2 mole ratios, one for each of the given reactants. Each mole ratio will contain one given substance and the unknown. Here's the first one. C3H8 is a reactant about which we know amounts, so it's a given. And CO2 is the target of our calculations, the unknown amount. The numbers in the mole ratio come from the balanced chemical equation. This 1 is from the coefficient before the propane, and this 3 is the coefficient before the CO2. Again, we have 2 givens, so we can construct another mole ratio. Here's the second. It contains a given and an unknown. The 5 comes from the coefficient before the O2, and the 3 from the coefficient in front of the CO2. We might need the upside down versions of these mole ratios, but we can't tell yet. The second step is to construct calculations, taking a given amount and multiplying it by a mole ratio to find the amount of unknown CO2, assuming the other reactions are in excess. This is the first calculation. We've used the given amount of propane and multiplied it by a mole ratio that contains propane and the unknown. Actually, this is the upside down version of the mole ratio on the left, above. The units cancel as they should, and the answer in this case is 420 molecules of unknown CO2 can be made from 140 molecules of propane. But we aren't done yet. We need to repeat the calculation for the other given reactant. Here's the second calculation. Our second given was oxygen, and it's multiplied by the upside down version of the right-hand mole ratio we wrote above. Again, the units cancel, and we can make 84 molecules of CO2 from 140 molecules of O2 if we have ample propane. Units cancel as they should. And we're done. What do these 2 answers mean? We only have enough O2 in this problem to make 84 molecules of CO2, so it must be the limiting reactant. Question 3. How many moles of NH3, ammonia, can be made from 6 moles of diatomic hydrogen and 8 moles of diatomic nitrogen according to the balanced equation 3H2 plus N2 making 2 NH3. Pause the video here and work out your answer. What are we asked to find? What information is given? We're asked to find the number of moles of NH3 and are given the number of moles of reactants H2 and N2. Wait a second. The previous questions have been about molecules, but this one is about moles. Don't worry. The same method applies to both kinds of questions because we know that chemical equations can be interpreted in terms of molecules or moles. Again, I'll label the givens and the unknowns in the question. Step 1. Write down 2 mole ratios, one for H2 and one for N2. Each mole ratio will contain one given substance and the unknown. Here's the first one. Hydrogen is a reactant with given amounts, and NH3 is the target of our calculations, the unknown. The numbers in the mole ratio, those come from the balanced chemical equation. This 3 is the coefficient before the H2, and this 2 is the coefficient before the NH3. Here's the second mole ratio. the one involving nitrogen and ammonia. Like before, it contains a given and an unknown. The 1 comes from the coefficient before the N2, and the 2 from the coefficient in front of the NH3. Step 2 is to make equations, taking each given amount and multiplying it by a mole ratio to find the amount of unknown NH3. Here's the first calculation. 6 moles of hydrogen multiplied by the upside down mole ratio that we wrote on the left above. Units cancel, and this calculation gives us the answer 4 moles of NH3 can be made from 6 moles of hydrogen. Next, we'll set up another calculation for the nitrogen reactant. Our second given was N2, and it's multiplied by the upside down version of the right-hand mole ratio we wrote above. Units cancel. This calculation says that we can make 16 moles of ammonia from 8 moles of N2. So we've arrived at our answer, or rather 2 answers. The results mean that H2 is the limiting reactant in this problem, and the maximum amount of ammonia that we can make, given the quantities in the question, is 4 moles. This is our final answer. Note that it made no difference whether we were calculating in moles or molecules. The method was exactly the same. Here's the next one. Question 4. How many moles of PCl5, phosphorus pentachloride, can be made from 0.044 moles of P and 0.204 moles of diatomic chlorine according to the balanced chemical equation 2P plus 5Cl2 making 2 PCl5? Pause your video here and figure out your answer. We're asked to find the number of moles of PCl5 and are given the number of moles of reactants P and Cl2. Don't panic about the non-integer amounts that have suddenly shown up. The method we've learned still works. Here are the givens and unknowns labeled in the question. First, we'll write 2 mole ratios, one for P and one for Cl2. Each mole ratio will contain the given substance and the unknown substance. Phosphorus is a given reactant, and PCl5 is our unknown. The numbers in the mole ratio come from the balanced chemical equation. There is a 2 coefficient in front of both the PCl5 and the P in the chemical equation. Here's the second mole ratio, the one for PCl5 and Cl2. Note I've written both of these in their upside down forms compared with last time, because I'm anticipating the next step, where I'll cancel each reactant in turn. To do that, the givens need to be the denominators in the mole ratios. Step 2 is to set up the equations. This is the first one, 0.044 moles of phosphorus multiplied by the mole ratio that we wrote above. The units cancel, and the result is that we can make 0.044 moles of PCl5 from 0.044 moles of P. This makes sense because they're in the ratio 2 to 2 in the chemical equation. Our second given was Cl2, and it's multiplied by the right-hand mole ratio we wrote earlier. Units cancel, and this calculation says we can make 0.0816 moles of PCl5 from 0.204 moles of Cl2, assuming that the other reactant is in excess. The calculations mean that P is the limiting reactant in this problem, and the maximum amount of PCl5 we can make, given the quantities in the question, is 0.044 moles. I hope you're getting the method here, and it works on molecules and moles, integer quantities and non-integer quantities. But very importantly, please note it does not work on reactants amounts given in grams. Convert these to moles first. Our last question for today. 0.250 moles of H2SO4, sulfuric acid, and 0.500 moles of NaOH, sodium hydroxide, are reacted. How many moles of Na2SO4, sodium sulfate, are made given the balanced chemical equation H2SO4 plus 2NaOH make Na2SO4 plus 2H2O. Pause here and work out your answer. Note that this question looks a little different than previous ones. Questions are not always written the same way, of course, but don't panic. We'll analyze to find out what we're asked to find and what information is given. We're asked to find the number of moles of sodium sulfate and are given the number of moles of reactant sulfuric acid and sodium hydroxide. In fact, this is an acid-base reaction. I've labeled the givens and unknowns in the question just like before. First, we'll write two mole ratios, one for sulfuric acid and one for NaOH. Each mole ratio will contain the given substance and the unknown substance. H2SO4 is a given reactant, and Na2SO4, sodium sulfate, is the unknown. The mole ratio comes from the balanced chemical equation. There's an invisible 1 coefficient in front of both H2SO4 and Na2SO4 in the chemical equation. This is the second mole ratio. Step 2 is to do the actual calculations, to set up the equations and calculate the amounts of products. Here's the first one. 0.250 moles of H2SO4 multiplied by the mole ratio that we wrote above. The answer is that we can make 0.250 moles of sodium sulfate from 0.250 moles of sulfuric acid. This makes sense because they're in the ratio 1 to 1 in the chemical equation. Our second given was NaOH. Here it's multiplied by the right-hand mole ratio above. This calculation says we can make 0.250 moles of unknown from 0.500 moles of NaOH. Did we go wrong somewhere? Why are both answers the same? The calculations mean that neither reactant is the limiting reactant in this case. Actually, the two reactants are present in stoichiometric amounts. You can probably see this from a review of the chemical equation in the question. We need twice as much NaOH as H2SO4, and those are the quantities that were given in this problem. So we did a calculation for nothing. But at least we know that the method works in limiting and stoichiometric amount problems, and it also gave us a little more practice with these types of calculations. Well done. Let's review. The first step is to analyze the question, to find the target of our calculations, and to identify the given substances. These sorts of problems are often written in words, and finding and organizing the correct information is often key. Write down mole ratios using the coefficients in the balanced chemical equation. You want to connect the target substance, the unknown, and one of the given substances. Set up your calculations like unit conversions. Use the amount of each given substance multiplied by the relevant mole ratio to calculate the amount of given substance. If you have two reactants and two givens, like we had here, you'll have two calculations to do. If you have three reactants and three givens, you'll have three calculations to do. That's it. The calculation that produces the least amount of product identifies the limiting reactant. And the maximum amount of product that can be made, usually the answer to the question, is given by the calculation involving the limiting reactant.